Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 414, Science and Space. I'm Ken Appel, and I'll be your host today. On this podcast, we bring in the experts, scientists, engineers, and astronauts, all to let you know what's going on in the world of human spaceflight and more. It's no secret that space can offer a unique perspective for researchers, but what exactly that unique perspective is sometimes is hard to grasp. When it comes to biological and physical phenomena, the microgravity environment, and sometimes lunar or Martian environment, can offer a new perspective on observations that help us understand whole segments of science. On this episode, we have Dr. Lisa Carnell, Division Director for NASA's Biological and Physical Sciences. She's here to help break down her side of the agency's science portfolio. Prior to her current position, Lisa has held a variety of roles inside and outside NASA. She worked on technology transfer NASA patents, served as Space Radiation Medical Countermeasure Lead, and served in biological and physical sciences as a program scientist for translational research. The PhD from Duke University holds 8 patents, has authored or co-authored several peer-reviewed journal articles, and has been honored with a number of prestigious NASA awards. I felt very fortunate to get a chance to speak with her. With that, here's Dr. Lisa Carnell on biological and physical sciences at NASA. Enjoy.
Minus 5 seconds and counting. Mark. Mission start. T0. Launch commit light circle correct. There she goes.
Houston, we have a podcast.
Lisa, thanks for joining us on Houston, we have a podcast today.
Oh, thank you so much for having me.
So in the show intro, I discussed a few of your previous roles and accomplishments, but wanted to rewind a little bit earlier to learn a little bit more about you. And can you tell our listeners where you grew up and what led you into the science field?
Sure. I grew up actually in Fort Dodge, Iowa, a very small town just north of Des Moines, and, literally worked the cornfields.
That is so Iowa. I love it.
I know. Every summer detasseling to earn money for school clothes, and, just incredibly valuable environment.
Yeah. Did you go to school in Iowa? Did you stay?
No, my family moved to Virginia while I was still in high school. So I finished there, and then I moved out to Virginia and ended up going to college in Virginia.
Okay.
So I did my undergraduate at Old Dominion University.
Did you? Yeah.
Yes.
It's close to Langley, right?
Yeah, it is. It's close to NASA Langley. Small school there. I allowed me to be at home and, kind of go back and forth. So, yeah.
I love that. Were you military? Was your family military or?
No, believe it or not. I was literally and figuratively the first off the farm. So nobody had gone to college in my family, and my dad was in construction, and there was only so much construction you can do in a small town, and the times were tough. So he moved out to Virginia where some of my family was, and got a job. It was booming, tons of construction going on. So then he moved the family out, and that's now what I call home.
What did you go to school for at Old Dominion?
So it's interesting. When I was growing up, I didn't know what I wanted to be. You look back at people's yearbooks and they say, oh, I want to be an accountant, or I want to be an astronaut.
It's like, how did they know?
Yeah. And mine was blank. I mean, I didn't know.
Yeah.
I was really fascinated with inventions. And I thought, I want to be an inventor somehow. And I'll be honest, I didn't even know what that was. So I went to the public library and would research in books and try to understand what kind of career that was, and led me to engineering. And so when I walked into Old Dominion and signed up, I said, well, I think I want to be an engineer. I'm not sure. And they were like, well, you did well in high school. Let's just put you in there and see where we go.
Sure.
So I studied mechanical engineering.
Got it. Okay. What led you to where you are today? I know that's a loaded question, right? Because talking about all of your previous roles, but was there something when you were studying mechanical engineering that sparked your interest in space?
Yes. So it was incredibly organic, the whole process. I graduated. I had done a co-op with NAVSEA, and I got to go work on military ships. I was helping to guide troubleshooting for gas turbine engines and steam turbine engines, and literally went on the ships and told them how to fix them. So this was long before females were even on ships. So it was a very different environment. I decided I didn't really love that, and I wanted to do something different. And I was really fascinated with the human body. And I thought, this is an incredible engineering marvel. It has everything. So I asked around, what could I do that has to do with, the human body itself in engineering? Biomedical wasn't very popular at the time. And so I created a program at Old Dominion and got my master's and did kind of merged like the kinesiology department with the engineering department. And I literally went and knocked on doors of doctors' offices and said, help me figure out a problem that you need solved. And I worked with this orthopedic surgeon in Virginia Beach. He was prominent in his field. He let me stand with him in surgeries and basically said, hey, we need to find a replacement for this polymer material that's the bearing. It just keeps falling apart. So I said, that's what I want to do. Well, looking at all the different ways you could modify it, they've been doing that. So I went to NASA and I said, hey, you've got some really incredible polymers here. Have you ever thought about using them in biomedical applications? And they said, well, we don't do that here. And I said, well, why don't we? Mm-hmm. And so I started a project there.
Oh my gosh. That was amazing. I love the way how you went from, baseline mechanical engineering, working with boats and things like that. What was that program that you had mentioned you were working with? What was it called? I
was a co-op for NAVSEA CENTLAT.
Okay, what does that stand for?
Naval Sea Support Center Atlantic.
Got it. Okay, so to go from that to be like, I want to understand the engineering of the human body. What was there? Maybe I missed this. What made you think of that?
That is interesting. I try to think back. My mind was always wandering, thinking about things, and I was just so fascinated with everything in engineering and how things worked. And I just kept thinking, the body has fluids, it has structure, it has electrical, it has every possible engineering aspect all in one place. And I don't know, it just kind of came to me in my thoughts.
I never thought of it, and I don't know if there's biomedical engineers listening to this and they're like, well, of course, but I just never thought of it as an engineering system. You've got all these different systems, and sometimes when you think about them and how they all work together so seamlessly, it's like, oh my gosh.
And it was so funny. I went to some professors and I said, I'm super interested in, the human body and, biomedical engineering. I'm much older. So biomedical engineering wasn't a very big field at the time. And they said, well, one of the professors said, Lisa, this is a really small field. It's not growing. And I said, well, I think you're wrong. I know nothing about this, so I think you're wrong. And I said, I think this is the most fascinating area. And he said, okay, you go ahead. And no kidding, I think a decade later, it saw a huge boom, just kind of as you see AI is now, front and center, biomedical engineering, bioengineering, just different ways that we can use biology to mimic materials. That all took off within like the next decade. And so now you see programs everywhere. It was incredible.
I think that, everything you explained is super inspiring for people, whether they're in college or whether, just chasing different, I would say, dreams or things that inspire them or things they want to do, right? Just ask the question is the first thing. The worst they can say is no. Let someone else tell you no type of thing. And you did that with not only NASA, but you had mentioned with the program with your master's. That's really, really cool. Okay, so I want to get into a little deeper about your previous roles and not totally understanding all the intricacies of the different scientific disciplines. Tech transfer, medical sciences, program scientists. Can you talk about those roles and how they led you to where you are now? So maybe talking about what you had mentioned with the polymer studies and how you got to NASA to where you are now.
Yeah. So I did my master's degree and I really focused in on a high performance polyimide at NASA. And a company came along and licensed that technology along with a piezoelectric device that had been developed there. And
is that where you step on it and it creates energy that way?
Oh, yeah. So it's a piezo. You got it. So piezo materials, which are really cool, and your body has piezoelectricity. So literally, so with these materials, if you press on them, they actually elicit an electric signal. And if you apply electric signal, they move. So this is a really key part because this really builds on my future. So I played with those a lot in the lab. I loved being in the lab. I broke things. I had a lot of fun. Blew a few things up. More of like materials just kind of flying everywhere. But had a great time and learned a lot. This company, Dominion Resources, the holding company of Dominion Energy, very large corporation, came in and licensed the polymer and the piezoelectric device from NASA, and they wanted to help move it out to commercial industry. And so they hired me to be the technology representative and actually develop prototypes for the companies. So I traveled the world. I was really young, traveling the world. I made prototypes for pacemaker companies, heart valves, player pianos, fuel injectors. I worked all over the place. It was incredible. I was super busy. I literally changed suitcases every week. Super fun. My best story of this and the outcome, for about 5 or 6 years, I worked really closely with Medtronic, and we would play with the polymer on how we could, coat it onto their lead wires for their pacemakers and defibrillators, because it had a really high dielectric breakdown, and they would coil it and they would crack, or these were failing in people. So, they could get a better material on it. Well, I worked with them. We got it to work successfully. It's now implanted in humans.
Right. Wow.
So it was a home run.
Wow. From heart valves to player pianos. Wow. Okay.
It's incredible.
So you were with them, and then how did you get back to NASA from there?
So I did this for so many years, and literally, I was getting exhausted. But in all the time, like I told you, my mind was always working. And as I was playing with all these different materials and things, and of course, my fascination with the human body, I thought I really wanted to do something that I felt was going to have a huge impact and help people. So I kind of married the idea of all the things I had worked with and thought, what if I could invent, so my nickname for them, jumper cables, for people that were paralyzed. If I used piezoelectric polymer fibers that were flexible and could send that signal across, maybe it's just the signal isn't making it across the junction. Maybe if I could bridge that gap with these jumper cables, it would help to improve people that were paralyzed. And so I wrote up this project description and went to NASA. By the way, Medtronic signed their agreement with NASA to use this technology, moving forward in their implants. On my wedding day, they called me to say, we've signed, good to go. And so then I put in my notice that I was leaving to go back to graduate school. So I went on to get my PhD to work on this project, to use everything I'd learned to try to help, people that had paralysis. So.
Sure. Okay. And so that brought you back to NASA, right?
Yep.
Now, what happened after you were done with that research study and your PhD?
Yeah. So during that research study, my PhD, I invented a lot of different things, the piezo polymers, and also extrapolated that to what I call my kids affectionately call the electric Band-Aid mom. Basically, it showed that it could heal wounds faster just by the piezoelectric response of the materials. But, sometimes you think of these things and, they don't always come together in the lab the way you imagine. You get these serendipitous finds like the Band-Aid. But I needed these fibers to be manufactured, and it didn't exist. So I had to invent that. How do I make piezo fibers? And so I was able to do that. I finished my PhD. They said, hey, if you want to go down this route, you're going to be here another 10 years. So I started working with stem cells and culturing them on my piezoelectric construct that I made. So I was able to drive those into nerve cells so that they could be used for transplantation. So crazy roundabout way.
Your path to NASA, yes.
And NASA paid for my education. I went to Duke University for my doctorate, and NASA gave me a grant to do all of this research. So it was fantastic.
You've been fascinated by inventions, and that's kind of what sparked you to get into all of this. 8 patents is a lot. Do you have one or two you'd like to highlight? I know we talked about the piezo polymers, the electric Band-Aid. Was there any other ones you wanted to highlight?
So a lot of them all built on each other, which is sort of interesting. Sometimes you don't go out. I didn't anyway. I didn't go out saying I want to be invent this. It was, oh my gosh, I need this material and it doesn't exist. So I had to figure out a way to make it happen. And so that resulted in a patent. The neat thing with that one, the piezo fibers, is that they could be used in a lot of things. We could weave them into suits, to make your spacesuit more piezo responsive and possibly, measure different things. So they're more electroactive suits. But then obviously my favorite patent, I would say, I think you asked, was the wound healing one. That one's exciting. It's licensed to a small company right now. So we'll see where they take it, but it was demonstrating some really strong results. And I think that has significance for people with diabetes. We tested it in rodents that had diabetic models, and it outperformed the gold standard. So I would love to see that happen. It would make people's lives so much easier with diabetic wounds.
That is amazing. I love the way that you explained how the patents kind of build off of each other. And that's something that we talk about with the space station science too, how it ends up building and, compounding. And so that totally makes sense on that front as well. Okay. Getting into your world and talking about your world of science here at NASA, BPS, or Biological and Physical Sciences. First, can you explain it to me like I'm 5? What is biological and physical sciences? Are we talking about them together or separate?
So we're talking about them separate, but It's really interesting because sometimes, things do couple.
Yeah.
So in the biological sciences, it's a really broad portfolio. We cover everything from all the way down to microbes, to plants, to animals, and 3D human tissue models. So we cover everything imaginable in biology.
That was the biology side.
Mm-hmm.
Okay.
And then physical sciences is huge too. So if you can imagine, my portfolio is massive. So we cover, fire, combustion, how do you put out fire and how does it start in space? It's very different than ground. Fluids we see the bubbles of fluids floating around in space. And we have materials. The way materials come together and form, crystalline structures are much more perfect in space. How can we take advantage of that? And believe it or not, I also have quantum in my portfolio. We have the Cold Atom Laboratory up on Space Station. So our physical sciences is a huge breadth of material.
What is fundamental research and why does it matter?
Okay. I get asked this question all the time. And it's interesting because a lot of people don't have that appreciation for fundamental research because they don't see the end result all the time.
Sure.
Because it's always, much earlier stage in the whole applied science field. So it focuses on increasing our knowledge and understanding of the way things work, or it leads to new basic principles of science. It paves the way for all the scientific breakthroughs that we see in the applied area and all of the technologies. So it's basically, if you think in the term of Legos, it is the base level building block for all of the applied sciences and technologies down the road.
What's an example of what fundamental research would be? I'm trying to think of what the word fundamental, and I think you did a good job of explaining that, kind of the baseline. I don't know, but when I think about it, I think we've done so much science and research. Is there still fundamental research to be done?
Yeah, that's a great question. Science never sleeps. Science is always going in, and you're never done, right? Because every time you answer a question, another question arises, which is very exciting, right?
Yeah.
But and you don't know what you don't know. And so that's kind of where this fundamental science aspect comes in, is kind of exploring the unknown and trying to, learn something new. Back in the days when they discovered CRISPR, the ability to go in and precisely edit genes using that technology, that was built off of fundamental research where they were trying to figure out how to, improve the growth of the yeast in yogurt. You know, who would have ever thought? Now we can use it to improve human health.
Why do we do research in space?
So the research that we do in space, we do it in space because it's impossible to do on Earth, the things that we're doing, but also as we want to be a humanity that explores and moves on an interplanetary, species, we need to understand how to live, work, and thrive in deep space environments. And so doing that research in space, not only does it help us learn more about, what we have here on Earth in different ways, but it's helping us, NASA, the human species as a whole, be able to take that next leap and explore.
Absolutely. And speaking of what you had just mentioned, places to do science and their benefits in the different places, what makes it interesting to perform science and research in all of those different or unique places, talking Leo, lunar, or Mars?
Oh my gosh, it's so exciting. We've been doing research in Leo on the International Space Station for 25 years now. And, we've learned so much in that short span, really. How do you live and work and thrive? And you know what? The question in the beginning, can humans thrive in a reduced gravity environment? Well, we've been able to demonstrate that, right? And so that's fantastic. But now as we move out to the moon or to Mars, we have different gravities that we have to deal with. We have different environments, whether it's more increased radiation, the atmosphere or lack of atmosphere. And so now we have this whole new problem set that we get to work on. Some people find it daunting. I think it's incredibly exciting. I love taking on those new challenges.
Are there benefits, or can you explain the benefits of, say, crewed interactions versus uncrewed research?
Yeah, so that's a really great question. We've had this discussion so much in my division. We started the CIRRUS program, which is called Commercially Enabled Rapid Space Science. And I think that's where we really need to go in the LEO environment if we want to, accelerate the pace of research. That's what it focuses on. And part of that involves the crew. So having the crew engaging with the experiments in real time and iterating just like you would in the lab on the ground. So when you go into the lab, if you see something like some of the examples I was telling you earlier when I was playing with materials, and I see something, I can tweak it in real time. Right now, the way we do our experiments, we send the experiment up, we get support from an astronaut, they work with the PI on the ground, and then they send the samples back for analysis. And then we repeat that. Well, it might be years before you can repeat it, or maybe you never do. You never really close the loop, and we can move so much quicker if we can do the analysis in space, send the results back to Earth, and we no longer have to keep sending the materials back and forth. Increases the pace of science, our understanding in space, and, really will start to move the needle in the direction we need to go.
You do a really good job of setting the context or the understanding of what biological and physical science type of research is. And so I want to ask, what are examples of those different type of BPS, biological and physical sciences research that's on the space station? But I thought a good way we could go about that is, can you walk us through BPS, your division's scientific goals? Is there any sort of framework or pillars? And then from there, if we walk through those and kind of understand, what type of research that is taking place and where.
Mm-hmm. Absolutely. So we created a framework for 5 key goals that we're taking on right now in my division, BPS. And that was shaped by the decadal survey that we received in 2023. And so we took a look at that, and then we focused on what the priorities were for moving forward for Moon to Mars. And we separated them out. Our goals are precision health. We have space crops. We all love that. How do you grow food off the planet? And then we have quantum leaps, all of the quantum science in space. We have foundations. So foundations covers all of our physical sciences areas, and then space labs. And space labs was fun and a unique one because predominantly our science has been done in LEO, in microgravity on the space station. And, space labs I brought forward and said, let's challenge everyone. This is doing science anywhere on any platform. So it could be on the moon, around the moon, out to Mars, in deep space, parabolic, suborbital. It's wherever we need the science to be done to understand at that level.
You had mentioned the decadal survey. Who administered that or put that together? Was that from the agency or outside?
So the National Academies of Science and Engineering and Medicine actually do the run and put the decadal survey together for us. So they solicit experts from the community and they get together, and it takes about 2 years. And they hold meetings and really try to gather the knowledge base on where we've been, how far we've come, and then where they think we should be going.
Okay. And is that for specific to NASA and how NASA can help the outside research community?
Yeah, so it is specific to NASA to help us shape our goals and where we're moving. And so from that, we were able to generate these incredible goals.
I did not realize that. Okay. Yeah. So you had mentioned the 5 goals, sort of the framework through BPS and your scientific goals. They are precision health, space crops, quantum leaps, foundations, and space labs. Let's go through each one. Let's start with precision health. And do you have a couple of examples of the research you're supporting with that?
I do. So let me just start with MABLE-B. So that stands for microgravity associated bone loss. So we all know bone loss is an issue for the astronauts in space, right? And so this experiment is really looking at the bone-forming stem cells and how those are modified in microgravity. And so we're really excited about that. It's actually returning, coming up here soon. So we'll get that science back and really be able to do the analysis. But one that we're so excited about is AVATAR, and that stands for a Virtual Astronaut Tissue Analog Response. And so AVATAR is actually flying on Artemis 2. And what's really exciting is that this is a first of a kind experiment where we're using cutting edge organ chip models. And these are made from the crew members themselves. So we got blood from each of the crew members and they were so excited to participate. It was incredible. So we've been able to work with them, create these bone marrow models that are going to fly right next to them. And when they come back, we'll be able to do a deep dive analysis on what happened and the changes in microgravity and deep space radiation. And then the Human Research Program is doing a study looking at immune biomarkers. Well, the immune system starts in the bone marrow. And so we'll be able to really do some correlation into, where the changes they saw and what we saw and how those impacts, are associated with deep space environment. What's also really neat about this is that these are individuals. So they're tied to each individual astronaut. So we have, we have some males, we have a female, we have all of these disparate individuals. So we get to see the individual response. So, Christina might be very different from Reed or Jeremy or Victor. So we'll get to see how individuals respond differently, which, this very early stage, but the end goal would be to allow us to send these out and eventually create personalized medical kits for crew members as they venture out into deep space.
This AVATAR research and the way that you explain it is amazing and super layered. How did this all come about in your work with it?
Yeah, so I couldn't be more excited about AVATAR. And serendipitous enough, it came together. Really, it built on one of my previous jobs at NASA, where I worked in space radiation and was a medical countermeasure lead, and was leaning in. And part of our strategy, in the strategy that I was developing, was to use organ chip models to start to screen and evaluate countermeasures for radiation. And so creating this opportunity to send AVATAR into deep space was really powerful and really built on my understanding and knowledge from the space radiation environment. So funny enough, when I was in that role as a space radiation medical countermeasure lead, I didn't know what I was doing. Let me just say, to be honest, I just knew it was something that was important that we had to do to help the crew and make sure that we protected them on these missions. And so when I was assigned to take this on and lead this area, I started by reaching out to other organizations and agencies that were already working in this space for different reasons. And so really have become close with BARDA, the Biomedical Advanced Research and Development Authority, all the different organizations at NIH and the FDA, and they've all become significant partners of ours. In fact, so much so when Avatar came about, they really helped guide me and helped me learn and educate me a lot in the medical countermeasure area for radiation. And so when Avatar came around, I went to them and said, hey, I'm going to do this incredible experience looking at deep space radiation and comparing it directly to healthy individuals. And they all said, I want to be part of that. And so these organizations have joined us in this mission and contributed substantially to it. And so they have a vested interest, and it's incredible. They'll be at the launch, and we're all excited for not only how this is going to help NASA move its mission forward to protect astronauts, but how we protect people right here on Earth from, nuclear events or other exposures to radiotherapy, and how you give them countermeasures to protect them from those aspects. So it's incredible.
Let's talk about second out of 5. I mean, there's no sort of rank, but we talked about precision health. Let's go over to space crops. Can you tell us a little bit about that from the BPS standpoint?
Yeah, space crops is great because we all relate to that. I don't know if you've seen The Martian. How do you grow food on another planetary body or the moon? And so the goal of space crops is to figure that out. So we have Apex 12 up on the space station right now, and it's taken a look at the changes in telomeres and how the stressful environments affect those. And then what can we learn from that to help, make the crops more robust so that they can grow in these really incredibly challenging environments. And it's building on, believe it or not, the twin study. I don't know if you heard about the NASA yet.
Yeah.
So
can you explain that to our listeners, what the twin study was, in case they don't know?
Yeah. And so the NASA twin study was groundbreaking. We had Mark Kelly on the ground. We had Scott Kelly, spending a year in space. And they're twins. So we were able to look at the changes and what happened to each of those astronauts. Well, Mark was a former astronaut and he was on the ground. But what happened to each of those individuals while Scott spent a year in space? And we saw changes in Scott's telomeres. And so that's really important. The telomeres, have a lot of implication. They can be associated with cancer and some other areas.
I was going to say, what are telomeres?
So they're at the ends of the chromosomes. And so they basically, they're like caps at the ends. And as they get smaller and smaller, then you get more damage is occurring. It starts shortening your telomeres. But what they saw were changes in the telomeres that were opposite and counter to what Mark was seeing on the ground, what we were seeing in Mark on the ground. And so we think these telomeres are associated with stressful environments in space. We see that in the plants. Would so when my team was telling me we're correlating, our plant stress with the twin study, and I said, well, that's an interesting extrapolation, but isn't that fascinating the way that you can do the cross correlation with life, right? Biology is not that unlike. It's really fascinating.
Sure. Wow.
But I did want to also highlight another really cool space crops experiment. And so we call it our ability to do space farming. It's called LEAF. So it stands for Lunar Effects on Agricultural Flora. And this experiment is actually sending plants down to the lunar surface. They're going to be in a container, so we're not planting them directly in the ground. But then we're going to take a look at how this changes in the partial gravity and the radiation environment on the moon that's going to help inform how we grow plants there in the future.
How are you able to track that once we leave?
We'll leave the hardware there, and we'll have cameras in there to watch them grow.
Got it.
So
Okay.
we'll be able to actually see what's happening, which is
cool.
great.
You've done a great job with, we've gone over precision health and space crops, 2 of the 5 different pillars of BPS science. And I love both the LEO, low Earth orbit, or ISS, and, moon, different studies that you're sharing. This is really, really good. Let's go over to quantum leaps.
Okay, quantum leaps. So quantum leaps is great. Right now we have a huge emphasis on quantum, in our country. It is incredibly important that we lean into this area. We've been doing some of the most cutting edge quantum research for NASA, believe it or not, in our division. We have the Cold Atom Laboratory. We've been doing this in space for a long period of time. And it's the first facility ever to study ultra cold atoms in microgravity. So it cools the atoms to near absolute zero. And this allows the researchers to study quantum phenomena in ways that you can't do on Earth. So this is the only one of its kind. It's incredibly exciting.
You mentioned quantum being a big focus, right?
Yeah.
And of course, it's AI, and now you hear all about quantum too. Can you explain quantum to our folks who may not understand just the very basic levels of what that means?
Yeah, so quantum is like really looking in at that next level. So think about Einstein and his theory with quantum and relativity and time disposition and the way but the way atoms interact at a different level than what what we can normally measure and that we can see. So for example, like we were able to measure for the first time a dual species Bose-Einstein condensate. And I'm just waiting for it because I know you want to ask me, what is that?
Yeah, you should just explain it now. I'm like, what does that mean?
What is a Bose-Einstein condensate? So this is like where a very small group of atoms act like a single large particle. And so we've been able to, they discovered them first here on the ground, but not in the dual. We've never been able to do a dual Bose-Einstein condensate. And we did rubidium and potassium in space, and we were able to measure those. So at the quantum level, things happen so quickly, it's really difficult to measure them. And so they slow down in the cold and in the microgravity environment. And so we can actually start to measure things at this, really, really, I can't even use a word, tiny level.
Let's talk about the next of 5 different research pillars with BPS. And let's go over to foundations. You mentioned this was more of like the physical science. Mm-hmm. Okay.
Yeah.
Tell us more about that.
Of course. Okay. And again, like I said, foundations is broad. So I'll touch on a couple of really key ones for us. So we're doing an experiment. It's running right now on the International Space Station. It's called ZBOT. It stands for our Zero Boil-Off Tank Non-Condensable Gas Experiment. And so this is a really important experiment. We're getting a lot of great data to understand cryogenic fluid, which is our propellant, right, and how it behaves in microgravity. So when they want to transfer cryopropellant, say, to another vehicle, some of our commercial companies are looking at doing that. How do you do that in a microgravity environment differently? And so the behavior of the fluids are different, and then you've got the heat and mass boil off that's different. And so we're able to make measurements in our system up in space station, and the data that we're collecting is fed into a model that all of the commercial companies are using to help model that system and improve their cryogenic fluid transfer and activity to get them out to Mars and beyond.
I love that. That's something we didn't even touch on was, supporting the research community, but also commercial space industry as well.
Yeah, absolutely. And that's huge right now, right?
Right.
It's a future.
And lastly,
I can't leave this one out because this is one that I just absolutely love. We have and you did a podcast with them recently, the flammability of materials on the moon. So you did a whole podcast, so we can direct folks to that. But literally, we're going to be sending a payload to the lunar surface that's going to let us see how combustion happens in partial gravity. It's
so
not
cool.
The same in microgravity, and won't be the same in partial gravity. But what's really neat about this one, it isn't just like, how does combustion work? We are working with the Mars Campaign Office and Crew Health to understand what material is of concern. And can we send that to the lunar surface, put it in the environment because they're going to use higher oxygen environments so that they can reduce pre-breathe time. So having it in this partial G, higher oxygen environment and a material that they are concerned about, and we can actually see it and test it before they send people.
It's crazy. You have to think ahead to problems we don't even have yet,
Yeah.
right? In this type of science.
Exactly.
Last but not least, let's talk space labs.
Yeah, Space Labs is so exciting because, and you've heard it kind of through each of the goal areas, where we've spent most of our time doing research on a parabolic flight as a precursor and using drop towers and then moving up into LEO. Now we're saying, okay, let's go to deep space. We're going to the moon. We're going on Eclipse lander. We're going to ride along with the crew in Orion. I'm ready for the next one, heading out to Mars. We are doing our science anywhere on any platform. And so that's a really unique way for us to gather the data NASA needs to support its exploration goals.
You know, talking continued research and things, you had mentioned the 25 years of continuous human presence on space station. What can we look to celebrate the space station and its contributions to BPS?
Oh my goodness. That's a loaded question because there's so much.
Yeah.
I mean, the success of the division, the knowledge that we've gained that's enabling NASA technology, enabling us to live and thrive in space, has been, thanks to the space station. I think it will be decades before we really start to fully appreciate it, the value that we've had from all of the science and the investigations we've done on the International Space Station, from understanding protein crystal growth to the way fluids behave. Everybody loves watching the astronauts, capture the fluids in their mouth or the bubbles that float around. That's a real situation that, they have to deal with. Fluids that behave different, It has been true stepping stone for our desire to live off Earth and be an interplanetary species. So I can't speak high enough of the incredible value it's brought to BPS and to NASA and the world, for that matter.
There's so much excitement for science on the moon and Mars. And what is BPS most looking forward to?
Oh my goodness. To be honest, I'm looking forward to doing more research out in deep space. I want to support the agency's goals of sustainable presence on the moon. And, with that comes from, helping ensure crew safety through, supporting the Human Research Program and their goals for countermeasures to protect the astronauts and developing personalized medical kits, to creating that greenhouse that will allow the crew to grow their own crops, on another planet. So I'm looking forward to how we can enable all of those activities and really be front and center in supporting the agency's goals.
As we move into more and more moon and Mars research, how does NASA plan to continue research in low Earth orbit?
Oh, that is a great question. We are poised in the fundamental research that we do in BPS to really support our new Administrator Isaacman's vision. He has really leaned into ensuring that we maintain American leadership in the space environment. And, that's what we're really set up to do, to realize the science and economic potential on the lunar surface and all of the different projects that I've described to you earlier. And then, increasing the rate at world-changing science discovery. And how's that going to happen? That's one of his pillars. How is that going to happen? Well, that's going to happen as we, also lean in towards this new commercial LEO economy, the low Earth orbit arena, where we're helping to foster that orbital economy. Another one of Administrator Isaacman's pillars, really leaning into that orbital economy. And we're doing that by working really closely with each of the commercial LEO destination providers. We talk with them about our utilization needs. And as soon as possible, we are putting our science on board every platform when they are available. So I'm really excited about what that means. LEO is a stepping stone for all of our future exploration activities. And so it's not going away. We really need that to understand and build upon the next iteration. And so really having NASA front and center is going to help to maintain the economic value in low Earth orbit, to really make it accessible for anybody that wants to do their research in space.
What would you like to share with young people curious about entering a strange new field?
Oh, so, I say go for it. Don't shy away from opportunities when they present yourself. Like I said, my path was so organic. And create, if you have ideas, and go create it, be proactive, go after it. I don't know where I would have been had I not knocked on the doors of doctors and, found my path, forward in the biomedical area. So, and when people come to you, and they offer you a project, and you're afraid, maybe you don't feel like you know what to do, you go for it. They didn't ask you blindly, take it on, ask for help. But I just say the biggest takeaway is just to go for it.
Lisa, thank you so much for joining us today.
Thank you. Thank you so much for having me. This has been a lot of fun.
Houston, go ahead.
Stop of the space shuttle.
Roger, 0J, and I feel fine.
Shuttle has cleared the path.
Became a feat for all mankind.
Actually, a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Never Houston, welcome to space.
Thanks for sticking around. I hope you learned something new today. You can check out the latest from around the agency at nasa.gov. We previously talked about the FM squared experiment on episode 386. And you can find our full collection of episodes and all the other wonderful NASA podcasts at nasa.gov/podcasts. On social media, we're on NASA Johnson Space Center pages of Facebook, X, and Instagram. If you have any questions for us or suggestions for future episodes, email us at nasa-houstonpodcasts@mail.nasa.gov. This episode was recorded on January 20th, 2026. Our producer is Dane Turner. Audio engineers are Will Flato and Daniel Tohill. And our social media is managed by Leah Cheshire and Kelsey Howren. Houston, We Have a Podcast was created and is supervised by Gary Jordan. Special thanks to Julie Laley and Megan Dorney for helping us plan and set up this interview. And of course, thanks again to Dr. Lisa Carnell for taking the time to come on the show. Give us a rating and feedback on whatever platform you're listening to us on, and tell us what you think of our podcast. We'll be back next week.
3, 2, 1.
This is an official NASA podcast.